So I'm going to record the first part of chapter 16. The only thing is I'm having an issue with this PowerPoint scrolling, so if you're going to see it in this editing mode right here and not as a PowerPoint presentation, unfortunately. So the first part is that we're going to have 16.1 is interpreting Earth's surface. Now we have a guiding principle that we use, which is called the principle of uniformity. And the nice thing about this is that it gives us kind of a baseline. Because rocks are changed today in the same way by the same processes that they've been changed for all of time. So if we can see how rocks are changing now, today, then we can also understand how rocks were changed back before we had geologists and those who were, or even recorded history. And we do know that we have catastrophic events that contribute in ways that we can't necessarily go back in time and know that a volcano definitely caused this, but we can make predictions based on what we know volcanoes do now and earthquakes do now, meteorite impacts, things like that. And so while we do have a tendency to be able to see that things don't change quickly all the time, we do know that there are events that can be considered catastrophic and make big changes in a small amount of time. So diastrophism is the process of deformation that changes the Earth's surface. It produces structures such as plateaus, mountains, and folds. And so diastrophism is a process that we see over time that helps to build mountains, produce plateaus, folds, things like that on Earth's surface. Now there's two different types of forces acting on rocks. One is stress, which is kind of what we're feeling right now with all this stuff going on with COVID. But the stress is the force that tends to compress, pull apart, or deform a rock. And then how a rock adjusts to that stress is called strain. So in this image you see right here, when the forces are uniform on a rock, there's not going to really be any changing result, but you have tension, which is pulling apart, compression, pushing down, and then shear. Those are all different types of stress, and then how the rock responds to that, breaking, things like that, is called strain. Now, sedimentary rocks, remember this was one of our three types of rocks in our rock cycle. They originate from flat sediment deposits, and so you can usually see them if you look in this upper right hand image, how the straight lines all the way across. So those are sedimentary rock layers, and we know that the rocks at the bottom are the oldest and the rocks at the top are the newest, because just like if you ever made one of those sand jars as a kid where you took the different color sands, you don't put the sand on top before you put the sand on the bottom. You start at the bottom and build your way up. Rocks do the exact same thing. Now, as far as weathering, we weather from the top down, usually. There are some exceptions to that, like volcano explosions, water erosion sometimes, but we know that the layers are going to be laid down horizontally or sometimes slightly angled, but that's because the Earth is flat, not flat as in the globe, but flat as far as our perspective being so small, it's flat. The curve of the Earth is not so significant that rock layers would also be curved, if that makes sense. So any sort of non-horizontal or very slightly angled bedrock means that something has happened to change that over the course of time, because that's not how rock layers lay down. Now, folds is one of the things that we see. So these are going to be bends that we see in the layered bedrock. They can look like waves, like S-curves, if you will. And you'll see one right here on the right-hand side. Even though you may think, well, these look straight to me, they are slightly curved, kind of in an S shape. And this is a result. Let's see if I can draw. No, not let me draw. Oh, well. This is a result of stress put on both sides of the rock pushing in. So because they're pushing in, the horizontal, kind of like a slinky, if you were to pull out on it and push in, I'm trying to think of another example that would be good. but it produces what's called plastic strain. And plastic strain is something that cannot be undone, meaning once I push on a rock and it breaks, I can't release that pressure, and then all of a sudden the rock goes back to being unbroken. It's inelastic, not an elastic like a rubber ball. It's inelastic, like breaking plastic, metal, things, wood, things like that. So when we have widespread horizontal stress on a large area, it produces what's called domes and basins. So this is kind of similar to the Black Hills Mountains in South Dakota, or you can even think of the Enchanted Rock in Fredericksburg as being kind of a dome-like shape. Now, Enchanted Rock has some other really interesting things going on with it that's not quite the same, but the feature, the shape is what I'm talking about. So in a folding feature, we have two different types of possibilities. We have the anticline, which is the arch-shaped, going to be the one on the right, where the younger stuff is on the top, the older stuff is kind of smashed in the middle. And then we have the syncline, which is right on the bottom left corner, and this is where it's shaped like a trough, or this looks to me like part of a PVC pipe. And you have the older rock that's kind of scooping on the bottom, and then you have the younger on the very, very top. So even though if you were thinking about the rock on the right, if I was to take a piece of rock, well, it's always going to come from the younger strata unless I'm really digging down deep. Whereas on the syncline, I could probably easily grab old or new rock and not really know. And so some of these features we can see on cliffs, like the Grand Canyon. If you've ever gone kayaking down a river that has really high cliffs, these things are really quite easy to see, and they're systematically the same no matter where you are on the earth, which makes them great principles to study rocks. Now, faulting is a really interesting process because it also produces a way for us to understand plate movement like folding. But faulting is produced by relative movement on opposite sides of a crack. So there's a pre-existing crack in the rock, and we have movement as a result. So when we're looking at a fault line where we have a crack, you can see here on the upper image, it's this dark black line that goes between the brown rock and the red rock. Now, there's a little person here, and the reason why there's a person in this mine is because the footwall is at his feet. So if you were to stand inside of a mine along a fault line, the rock that's at your feet would be the footwall, the mass of the rock below you. Now, the head is going to be pointing towards the hanging wall. The wall that would be above your head, if you're standing on the fault line, is going to be called the hanging wall. And then the fault plane is that black line that runs in between. Okay. Now, if you've ever seen I'm going to forget the name of the movie, about the Venezuelan miners, and I'm probably not saying that in a way that's clear, that I'm not talking about your age, but I'm talking about the miners that were trapped. I think it's called the 33. Oh, let me see. I'm Googling it right now on my phone. Movie. The 33, and that is my favorite number of all time. But in that movie, it's a really great movie. If you haven't seen it and you have lots of time at Amazon Prime, go watch it, because in the movie it talks about some of this stuff that's really pertinent. Not appropriate for elementary school kids, but I find it really fascinating as an adult to see kind of the status of people in other countries. And I'm not even sure what they're mining for in Venezuela in this particular one, if it's coal or precious metals, but go watch it, the 33. Highly recommend it. Now, if we're looking at the bottom left-hand picture here, you can see there are two red lines drawn in, and the red lines are meant to show you kind of where the rocks used to be matched up, like playing dominoes, where they match up. Well, where they're sitting now, they don't match up. The rock on the left appears to either have fallen down, or the rock on the right has appeared to either been pushed up. And that kind of stuff we don't really know, just based on this image, if one's falling down or one's pushing up. But you can see the fault line is that crack right there that runs between them, and very, very clear. So if you were to be standing on the fault line, the rock on the right would be your footwall. The rock on the upper left would be your hanging wall. And the fault plane, the fault line, is that crack that runs kind of from the bottom left-hand corner to the upper right-hand corner. Okay, so you need to be able to draw, or at least I say draw, but I don't know if we'll be back before the next test. But you need to be able to identify the features. I'm going to try to get to get better test banks. I had to handwrite all the questions to get better test banks with images for you on this next test, because this kind of stuff, geology, is a little bit more helpful to have images. So now we're going to have 3 different types of faults, and so these are still pertains to the hanging wall and footwall, but in a normal fault, because the plates, if you look here on the right, are pulling apart, so it's a tension pulling them apart. The hanging wall is going to move down relative to the footwall. Okay, so they're pulling apart, and the rocks are essentially going to fall down and create that fault line. Now, a graben is when you're going to what you produce in B, where the plate pulling apart, there's actually 2 kind of fault lines, and what results is in a middle section essentially falling out there in the middle. And this is, I believe, over in the Sierra Nevada mountains. We have grabens and then what's called horsts. Now, horsts are also produced because things are being pulled apart, but when they're pulled apart, the bottom 2 will fall down and the upper middle part stays up. So they kind of happen in sequence. Horst and graben kind of alternate. And so it says the block surrounded by the normal faults is going to be lifted up in comparison to the side pieces. Okay, and if you think they look like sharp pieces of cake maybe right now, but over time they become smooth rolling mountains, which are really beautiful features. So other faults, the other 2 kind that we have are the reverse fault and the thrust fault. The reverse fault is going to be because we're having a compressional force or stress on the rocks, pushing them together. And instead of falling down, since you're pushing on them, one of the rocks, the hanging wall, is going to be pushed up. Okay, so imagine pushing something up a mountain. It's going to be pushed up. But the hanging wall and the footwall, those things don't change because that's person perspective. Standing on the fault line, my hanging wall is still above my head. My footwall is still down at my feet. Anderson, stop. He is pushing his head into my 15-year-old cat right now. Please stop. Be nice to Virgil. Okay, you're petting him now, so please stop. Oh, okay. So a thrust fault is going to be a reverse fault. So still the same. The hanging wall is going to be pushed up relative to the footwall, but there's a very low angle. So if you look at it, it's kind of like taking a smaller chunk out of the top of the rock and only a small piece is pushing up instead of that very deep angled crack that we see in the other 2 faults. Okay? So that's the only difference. All right, let's talk about earthquakes, and then we will pause this video and do the second half-ish of this slideshow. So earthquakes are defined as quaking, shaking, vibrating, or upheaval of the ground. Okay, so the ground can quake, shake, vibrate, or be upheaved. Upheaved? Upheaved. I don't know if that's a word. The results, or what earthquakes stem from, is the sudden release of energy from stress on rocks. So the pushing, the pulling, the shear stress, eventually, if there's enough energy built up behind that, the rocks are going to move very quickly, and that movement of something very large that's underneath us is going to result in a very significant feeling. Now, vibrations are considered seismic waves. So we talked about P waves and S waves, Rayleigh waves, Love waves before. And this is what we're talking about. Now, most all earthquakes, I don't know the exact number, but I would say probably 90% of all, I don't know, I would change that now with the amount of drilling we're doing. But I'm still going to say most all, 90%. Of all earthquakes occur along fault planes when one side is displaced with respect to another. So in San Andreas faults, remember that buildup of those 2 plates moving past each other. Eventually they're going to snap real fast, and that snapping is what produces the earthquakes in that area. Now, the elastic rebound theory is, so you see the San Andreas fault here, that says that when 2 plates are pressed tightly together, and the friction between them restricts motion, meaning like you're pushing your hands together so hard that you actually can't move your hands past each other. The stress will continue to build up until either the friction or the rock rupture strength is overcome, meaning the stress becomes so great that the rock then is just forced to move as a result of the stress. The stressed rock will snap suddenly into a new position, but that force between the plates is still not going to go away. It's just going to be slightly lessened, like a bad headache. Taking one Tylenol, the headache is eased, but it's still there. So it doesn't really ever go away, which means it's just a matter of time until the next earthquake occurs. So locating and measuring earthquakes, there are two really important definitions on here. I feel like I've seen this before on TEKS exam questions, and so we have the definitions in here because they're really important to know the difference between. So we have the focus and the epicenter. So now the focus is going to be the actual origin of the seismic wave underground. Okay, so it's underground. We're not underground, it's all the way underground, the exact origin of the plates. The epicenter is directly above the focus, but the epicenter is on Earth's surface. Okay, directly above the focus, but it's where the epicenter, the very center, beginning, the origin of all the waves on Earth's surface. Okay, so even though they are right above each other, the terms refer to different things. The focus is underneath Earth's surface, the epicenter is on Earth's surface, but they're both going to be the origin of the earthquake, just at different places. Now, the seismometer is the instrument that we use to detect and measure earthquakes, and they have these all over the world, mainly at laboratories that are meant to, that are monitoring or studying Earth's type of earthquake activity, seismic activity. But that's not always the case. Governments have them, private labs have them, academic institutions that are just near places where there tends to be earthquakes will have them. You could make a seismometer if you had a sensitive enough equipment. So the seismometer is an instrument that's used to detect and measure earthquakes. And so we do know that there's a baseline of movement. Plates are always moving. There's nothing we can do about it. We're floating on a liquid layer beneath us. However, they can monitor fluctuations, increases and decreases, and predict, based on what we know, when an earthquake might occur and the size of the earthquake. So these seismometers usually detect three kind of waves: P waves, which are those longitudinals, S waves, which are transverse, and surface waves, which are up and down. They can hear that on that, so don't do the gun in here right now. Measuring the earthquake strength, we do have a scale that we use, which is the Richter scale. Now, the effects of an earthquake could be very minor to very major. Structural damages to buildings, fires because of downed power lines, natural gas explosions, things like that. Not necessarily fire because there's an earthquake, but fire because of the man-made aspects on Earth's surface. Landslides, so the loosening of dirt, displacement of land surfaces, upheaval, and then obviously tsunamis and tidal waves. And tsunamis is going to be the beginning of our next. No, we'll cover tsunamis and then take a break. So tsunamis are a tidal wave. Now, the Richter scale is based on swings in the seismograph recordings. It's a logarithmic scale, 10 times stronger between all of the whole numbers. So between 0 and 1, it's 10 times stronger. Between 1 and 2, 10 times stronger. So then between 0 and 2, it would be 100 times stronger. The number increases with the magnitude of the quake. So the more intense, the higher the number. 3, a magnitude of 3, is usually not even felt by us. You can see it says felt a small earthquake, but no damage occurs. 9 is the largest we've measured so far. So that's an important distinction because this means that there might be more powerful earthquakes out there. We just haven't measured them yet. So there's always adjustments that are going to be made to this scale. So if we look at it, we see that 3 to 4 is felt as a small earthquake, but no damage occurs. 4 to 5 is minor earthquake with local damage. 5 to 6 is moderate earthquake and structural damage. 6 to 7 is strong earthquake with destruction. 7 and 8, major earthquake with extensive damage and destruction. And then 8 and 9 is great earthquake with total destruction. And so now the thing about some of these scales that makes it a little bit difficult is there what's called the Mercalli scale, and that's based on destruction that's observed, like pictures fell off the wall, or windows were broken, or 3-story buildings fell, that kind of thing. It's used to classify earthquakes based on what we see. The problem with those types of scales is that not all building codes are the same. So in California, they have very strict building codes because of the high incident rate of earthquakes. But if you go to somewhere like Haiti doesn't have the building codes that we do in California. Therefore, if an earthquake that hit Haiti was the same size as California, it may not do as much damage as it would in Haiti, just because the building codes are different. So the Richter scale is more systematic. It's not subjective, it's more objective. And so just to let you know, there is another scale out there, but it's a little bit more subjective than the Richter scale. Now, a tsunami, the definition is a very large ocean wave, which sounds like a very simple definition, but it is generated, and you can add this to the definition, generated by a very strong disturbance in the ocean floor, usually the result of an earthquake. Okay, now it says here earthquakes, landslides, and volcanic explosions can cause them. Volcanic explosions can cause them. I think that was a concern with the Hawaiian volcano explosion last summer, 2 summers ago, don't remember when exactly. But earthquakes are probably the number one creator of tsunamis. And there's another great movie about the tsunami over in, I don't want to say Fiji. It was in 2004. It says the Indian Ocean, but that's not right. Thailand. Okay, that's where it hit. And the movie, if you haven't seen it, it's called The Impossible. I'm just giving you all kinds of movies. 2012 movie, so not that long ago. You guys may have seen it, but so good. It talks about the tsunami that hit Thailand, I think the day before Christmas Eve in 2004. And, I mean, they were completely caught off guard. But if you want to see the powerful effects of a tsunami without having to live through one, you should watch The Impossible. Such a good movie. And so speeds of up to 725 kilometers per hour, which is 459 miles per hour, which we don't really understand how fast it is because we can't really travel that fast. But essentially what it means is water is coming in so fast it literally can wipe out trees, can wipe out buildings. And so people and small animals and big animals, boats, cars, they're of no consequence at all if they can take down trees and buildings and big, big, big objects. The wave height can be over 25 feet. I don't know the height of the tsunami wave that came into Thailand, but I do know that it was incredibly destructive. In fact, it resulted from a 9.1 earthquake based on the Mercalli scale, which is not the scale that we just got done talking about. But over 200,000 people died. Mostly the people just were not found. And so that's how they calculate the deaths. That's how they estimate them, just because they really don't know. But the tsunami itself, it says, was 15 to 30 meters tall. The maximum height was 51 meters at some point. So very, very, very powerful tsunami, very destructive. And they can have very long wavelengths. And the thing about having very long wavelengths is that sometimes people miss the power of it because it seems like, well, if it's got long wavelengths, it's really slow. But what that really means is a really big wave is coming in at the same time. And so sometimes before a tsunami occurs, what they see is the ocean recedes because the ocean is basically sucking in all the water, creating this big wave before then it rolls back in. And so you do see that in the movie. Again, I really recommend it. After you finish this slideshow, you should watch The Impossible. But be prepared to cry because it's very sad. But just a very tragic thing. And it tends to happen in countries where, so if there's an earthquake on one side of the world, then the tsunami goes the other direction. So normally you're not hit by an earthquake and a tsunami. But I know Hawaii's had a tsunami warning before as a result of an earthquake, I think over in Japan. So normally they're close by each other, but they're not usually going the same direction or happening in the same place. Okay, I think that this video ended up being a little bit longer than I wanted it to, but I'll finish up the last 12 slides or so of chapter 16 in a second video, so please make sure you do come back and watch the second video.